speaker is Lei Li from the University of Oxford, who's going to tell us about AI-powered multimodal cardiac data analysis towards cardiac digital twins for personalized healthcare.
Thank you so much for the kind of introduction. I'm Lei Li, and it's a great honor to be here to present what I have explored in the AI-powered digital twin. Honestly, currently I'm quite nervous and hungry, so I will try to speed my presentation, and so you can have lunch as soon as possible. I suppose the audience are already quite familiar with the concept of cardiac digital twin, which employ the patient-specific data for the virtual heart modeling. And my research interest is specifically focused on developing AI model to advance the virtual heart modeling. And today, my talk will cover these two diseases, atrial fibrillation and myocardial infarction. So let's start from the atrial fibrillation. So atrial fibrillation is the most common cardiac arrhythmia, and for the to improve the treatment outcome of the atrial fibrillation, usually it's very important to know the distribution of scar within the atrial surface. And to achieve this, we need to employ the image data like LG, MRI to do the automatic segmentation and reconstruction of the geometry. So during my PhD, I spent many years working on this. And the general pipeline is start from the cavity segmentation, and then wall segmentation, and then final is the scar segmentation. It's like a cost-to-five procedure. However, the scar segmentation will be very challenging because, as we know, the wall is quite thin. It's only about 1 to 2 millimeters. And the idea I proposed is that why not we just skip the segmentation of wall, but directly project the scar onto the left atrial surface. So the general idea is that we can imagine a 3D volume, and the z-axis is the wall thickness. And what we have did is project this 3D volume onto the top surface. So by doing this, we can still see a very clear distribution of the scar, even though we lost the information about the thickness. But in clinical, the doctor told us that in clinical, they more care about the distribution of the scar instead of the thickness. So based on this core idea, I did a series of work, and today I will introduce two of them. So the first one is that I designed a framework which combines the multi-scale CNN with the conventional graph cast to do the scar segmentation. So it starts from the target image, which has already segmented with the left atrial cavity, and we can obtain its contour. And the thing we can do is that we can extract the patches along the normal direction of the contour. At the same time, we can create a 3D mesh. So within the 3D mesh, we know the node and also its neighbor. So we can solve this, we can convert this segmentation problem into a graph cut optimization problem. So instead of using the conventional intensity and the distance between different nodes information, we propose to using the neural network to directly predict these two ways for the graph cuts. And by doing this, we can learn more advanced features. And then we can employ the MaxFlow to solve this objective function and get the final scar segmentation. So here is our results. We can see that the top left is our prediction automatic segmentation, and that side is the ground truth. We did a lot of comparison experiment and also ablation study. So in general, our results is quite promising. We can see it's generally matched with the ground truth. Even though it's a little bit over segmented, it's because of the graph cast property. And here is the 2D segmentation results. It's also generally matched well with the ground truth. So this is our one methods. Another thing we start to explore is that we notice we want to apply our model onto multi-center data, but our model is AI-based, and it's very sensitive to the domain shift. As we can see here, if we have different domain from different center, and if we train a model, it can be perform very good if we training data include the center 1, or if we include the center 1 to 3, but it still cannot generalize to center 4. So the thing we hope to explore is that whether we can train a generalized model which can perform even for some unknown domain, which we cannot see when we train our model. So it can be generalized to a new center. So that's the general idea of we want to achieve. And for the specific application of the multi-center LG-MRI, we see that we collect different center data, and we notice this data, they have different distribution in the intensity level. Moreover, we also notice that different doctor from different center, that when we label their the left atrium cavity, they have different criteria. So which result in we also have label shift in the multi-center data. So to get a very generalized model, we need to consider these two different shifts within our multi-center data set. So the thing I did is, the first thing I did, I create an evaluation model to explore like how large the domain shift and how it will affect the final segmentation model, and how the current generalization methodology can solve this problem. So this is the evaluation model. Besides, we also designed a model which can solve both the domain shift and label shift issue. The general idea is that we will train a global model from the multi-center data, and we try to think a personalized one for each center by modifying the global results. So here is the results for the evaluation model. We can see that we evaluate different semantical segmentation model, and we can see that once we introduce, so the orange line is the model trained on a new center. So we can see a very evident decrease when we employ the trained model on a new center. So that's the thing we want to solve. And here is the results for we test on the currently employed domain generalization methodology. We can see that after introducing like a HM is a histogram matching and modality disentangle and the random style transfer, this kind of methods all can improve the model's generalization ability, but it's still a little bit worse than the original performance. Is about like 0.9. So we still can do a lot of exploitation to improve model's generalization ability. So this is a work about atrial fibrillation. And for the Markov function, I also did a lot of work on combining different MR sequence to improve the pathology segmentation. So today our topic is digital twin, right? So it's not for the image. It's not the only data. We also have the ECG data. For instance, they already have some studies prove that it's possible to directly identify the location of the myocardial infarction directly from the ECG, but it's not very accurate because we do not have anatomical information from the ECG. So based on this observation, the next thing I'm trying to explore is that whether we can combine the image data and the ECG data to identify the location of infarction. So then I know the concept of cardiac digital twin, and so based on the definition from Carrio's paper, she separated the cardiac digital twin into two phases. The first phase is anatomical twin, and the second is the functional twin. So the anatomical twin is to do the modeling, 3D mesh reconstruction from the image, and the functional twin is to do the ECG simulation and also the personalization. So with this digital twin framework, I'm trying to answer two questions. The first question is that whether, like, how the myocardial infarction distribution will affect the ECG morphology. And the second question is that whether we can inversely infer the myocardial infarction location from the ECG. So to answer these two questions, I try to create a digital twin model. So we employ the image and to extract contours and employ the statistical model to create the torso geometry, and we can identify the location of the electron nodes. And using similar strategy, we can also do the biventricular segmentation and also the geometry reconstruction. And to consider the subjective, the anatomical variability among different subjects, I projected the model, the 3D geometry onto a consistent about ventricle coordinate system. So by doing this, we can represent the infection distribution unifiedly for different subjects. So for example here, I did a sensitivity analysis. I consider different scenario by varying the Markov function location, size, and also the transmural extents. So here is an example. We consider different location and also different size and different transmural extents. So this is the anatomical twin, and second thing is the functional twin. The simulation tool we employ is the iconal model, and to consider the effects of the malfunction, we vary the conduction velocity for the infection in the healthy area. So here's the results we got. So we can see that after introducing the malfunction, we can see a slower propagation of the signal in the ventricle, and it can also result in the final morphology change for the ECG for the QRS. So to evaluate whether our simulated QRS is realistic, we investigate whether we generated the QRS is consistent with the literature reported QRS abnormality. So in general, we found that like for all these abnormalities, we can get some consistent results as reported in the clinical besides the pathology Q-wave. Another thing we did for the sensitivity analysis is that we calculated the dissimilarity between the Markov function QRS with the baseline one, which means they do not have any scar on the geometry. So in general, we can see that almost all these scenario can be look different as compared to the baseline, and some scenario like some location has more evident morphology change compared to the others, and the transmural and the larger malfunction will result in more evident ECG morphology change. Besides comparing with baseline, we also compare with each other different scenario. By doing this, we can these results can give us some confidence that it's possible to distinguish different scenarios. So now we can answer the first question. The Markov function, location, size, and transmural extent all will affect the ECG morphology. And now we are trying to answer the second question, is that whether we can inversely inform the Markov function distribution from the ECG. So the model we employed is quite simple compared to the former two speakers. It's purely data-driven. So the general idea is that we designed two variation autoencoded model and separated encoder where to extract features from the point cloud and QRS, and we concatenate them together for the inverse inference. So even though our model is simple, the results is kind of promising. So we can see here, the left side is the ground truth and the right side is the prediction. In general, our model performed very good besides two scenarios, which is quite reasonable because when we do the sensitivity analysis, we realize that these two scenarios, like these two locations, the simulated ECG is quite hard to distinguish with the baseline. So which, of course, can result in the inverse inference results is not that promising. So besides that, we also explore like what's the limit of our model for smaller size of the infunction. So here is sensitivity analysis. We can see that when we decrease the size of the malfunction at the same location, the morphology change becomes slower. And this can correspond and result in the inverse inference morphology performance change. So in general, we can see that unless as long as the radius of the scar is larger than 0.2, the performance is generally good enough. So so to conclude, we can answer the second question. So yes, it's possible to inverse inform the Markov functions using the AI model very efficiently. And finally, I want to give a quick conclusion about the digital twin. So we know we have anatomical twin and the functional twin. So for now, I did a lot of work on the anatomical and pathological segmentation, and now AI model can solve this kind of issue very well. But like for the 3D, especially plus 10 dimension for mesh reconstruction, I think we still developing the powerful AI and the stable AI model to achieve this. As for the function twin, the former two speakers has mentioned a lot, like we can develop sensorial model using the, like for instance, the PIN to achieve more efficient ECG simulation and also for the personalization. So finally, I put a GitHub link here. So I try to summarize the resources related to the cardiac digital twin. Because I'm actually a new learner for the cardiac digital twin, I think it's very helpful to combine all the resources I can find. And it can helpful for the future learner of the interest in the cardiac digital twins. So that's all the content of my talk. Thank you so much.
Thank you so much. Very nice talk. Open for questions. I have a couple of questions. So very nice that you show that you can identify the MI size with the ECG, but that depends on the size of the heart. If you change the size of the heart, the thickness of the heart, or different structure, how does that relate with the size of the infarct?
You mean the relationship between the inverse inference results with the size of the infarct?
Right.
So I think it's so this slide shows the results. In general, if we decrease the size of the infunction, the performance will also affected. I think it's reasonable because the size of the infunction area will affect the morphology change of the ECG. If it's hard to distinguish with the baseline, and then it's hard to inverse inference the location of the infunction using the AI model. Yeah, that's kind of their relationship.
All right, good.
Thank you.
Other questions? Okay, another question. How do you model then in the ECG? We still don't know exactly what produces the T wave in the sense of is the dispersion in the difference between epi to endo or base to apex. In your simulations, what was the difference that you used? You use variation in the epi to endo with thickness on the M cells, or more base to apex, or you try both?
I think it's a little bit hard for me to answer the question. You are asking like what's the variation in the apex and the basal when we do the simulation?
Right. In order to get the ECG.
I guess maybe my co-operator Julia can answer this question because the simulation tool I used is from him.
Okay.
Yeah.
So be much work. Okay.
Okay. Thank you so much.
All right. Any other questions? All right. Well, let's thank Lei Li. Thank you so much.